today a few good anachronisms. Thanks.
Thank you very much. Hello, everybody. I've been here for a while now and seen an awful lot of stuff that was too hard to read. We're all getting old, we can't see so good. I'm not going to make you read anything. I have put my talk onto these post-it notes. Only I can read it. Thank you. Okay, I've put up the beginning of the talk this cartoon picture. It is in reality a picture of our two children about 45 years ago when they were going through the period of being with the little boys and investigating things. And especially the younger one with the black hair was pretty adventuresome investigating everything in the house, and the older one was kind of dismayed about it sometimes. So I thought really for a long time for a word that describes this younger kid, and I never found a good one in the English language, at least in the official dictionary of the English language, because they were all kind of pejorative. You know, he was being naughty here, but I don't want to say that he was being naughty, because he was really being curious. And the word I finally came up with after a long, long time didn't come from American English, I don't think. I think it came from British English. And I think it's basically only a slang word because I never really actually found it in a dictionary. But this kid does stuff that is dodgy.
Yeah, dodgy. That's British English.
Yes, thank you, Peter. That confirms my thought about it. Well, he's always doing things that are just a little over the edge, you know. He's tweaking things, he's trying things, he's investigating things, he's having a good time. And the other kid is a little bit dismayed about it and thinks maybe he should be brought under control a little bit, or at least reminded of the rules of appropriate life. So they make a pair. And today, looking back on that picture, it kind of makes me think of Albert Einstein is like the kid with the black hair, and his friend Mikhail Besov is like the kid with the white hair. It does kind of sometimes calm Einstein down a little bit or suggest a direction he should look in or whatever, but Einstein was kind of a force to be reckoned with, and he went about and did things that you can only describe as dodgy. And in particular, I think that second postulate in special relativity theory is a little bit dodgy. And my second postulate, I think those names get switched around between different ideas that we had. But the one I'm referring to is the idea that the speed of light is the same constancy with respect to the observer in every inertial reference frame, because he doesn't actually say everything that people in fact rely upon when they apply any of this theory. He just quietly left part of it out, and that is dodgy, to leave part of it out. The part that he left out was an assertion that this statement about the speed of light applies over the entire propagation path of the light, no matter how long that might be. Now, it might be okay if you were talking about something nearby on Earth, like a laser source. It might still be okay if you're talking about the sun. It's a little dodgy when you're going beyond that and talking about maybe some distant planet, or worse yet, some distant star, or worse yet, some distant galaxy, or worse yet, infrared photons alleged to be from the Big Bang. Now, can we really believe that light arriving to us on Earth has been traveling at speed c relative to us throughout the entire time of creation? That just seems awfully, really over the top. We are really being exhibiting the absolute ultimate of what you would have to call anthropocentrism. That's what we had for science before we had science. That was before all those great guys like Galileo and Newton and Copernicus and Kepler and all the rest of them, when it was a cosmology written by the church. And the people were basically at the center of the thing, and everything was relative to them. And they sat there and they saw this marvelous sky that went by every day, went around them, and it was really symmetrical, and in addition to that, it had a few oddball wandering stars for them to think about. And they were really being entertained by God. I find it difficult to believe that, and I don't think that that's the appropriate kind of assumption to put at the base of a scientific theory. So I want to kind of wave a finger at Einstein over that overstep, as I regard it. Let's start over. Instead of starting with a postulate like that, that's, oh, I see a question.
Do you wave the same finger at Newton for his universal law of gravitation?
No, because that wasn't really making an assertion about the behavior of light, and that's what I'm particularly concerned about, because that was at the root of special relativity theory. I think Newton's theory didn't have any business about signals going from one body to another body, and I would regard that as simply an omission rather than a mistake. So, I think we need to look into that and possibly find something more sensible to do, and possibly redo special relativity theory accordingly. Now, you can tell that this really stuck because it was already in place even before Einstein came along. In the years before he published his first paper, people were getting into electrical science already, and they were studying every kind of aspect of interaction between electrical charges, and they were formulating pretty sound mathematics about it. And everywhere you look, you will see terms in the mathematics of the form R over C. And that means a distance over which a signal has propagated, and this assumes speed c of the signal. So embedded already in what they're writing down is the assumption that we're talking about c relative to the observer who's taking the data. With Einstein, you add to that lots of expressions in the form v over c, where you've got velocity divided by the same presumed constant. And even after Einstein, the continuing development of atomic energy and everything involves mc squared. So again, the c is just being treated as a constant, and they're not putting any attention to how it might vary by means of the reference to which it is tied when we're talking about some kind of long propagation path. So this has just been totally ignored. Now, in the written paper, I try to account for at least some reasons why this may have happened. And among these reasons, I see that, first of all, some things were missing at the time. Some things just hadn't happened yet. One thing that I believe to be important for the proper development of a relativity theory is information theory. After all, relativity theory is really about signals. It would be a good idea to know something about signals before formulating that theory. And what was absent at the time of Einstein was the idea that a signal would need to be something of finite energy. You cannot make signals really out of waves that continue forever. Waves like that don't convey any information, they just stay the same. It's like a monotone, and it tells no story. So in order to have any information conveyed, there has to be some variation, and at the root of it, you have to put together that variation by having things that are really more pulse-like and not just continuing waves. And you can't just do it with Fourier analysis because there's that coupling in electromagnetic theory between E and B. So it's a little bit complicated, and you need to take into account all of it in order to get a meaningful theory. There was another thing missing, I think, only because it came way too early, and may not have seemed as important to Einstein when he studied as a boy before he matured and became more of a scholar and when he was a kid like that kid. And that would be Euclidean geometry, because Euclid expends a great deal of care on the idea of being careful with making postulates. You don't just make up postulates and stuff them into an existing mathematical system. You can, if you've constructed a mathematical system that is really sound, and then you stuff another postulate into it, you're probably going to create trouble. you're going to create paradoxes. Did anyone ever hear of any paradoxes in special relativity theory? Well, that happens. So that's one problem. And he, I don't know why. Maybe he was too young when he studied geometry, didn't pick up on that and worry about that sort of thing. So that was excusable, perhaps, especially because information theory hadn't been invented and Euclidean geometry may have been sort of forgotten. There's a third part, though, that I don't understand, that really didn't get adequate attention in the construction of special relativity theory, and that is the fact that there was a pretty well-developed body of mathematics at that time about using differential equations and boundary conditions and just cranking the wheel and solving problems. So here we got a problem like that. It's got Maxwell's equations and differential equations, and it's got boundary conditions. There is a source and there is a receiver, and you can just plod along and solve the problem and find out something about it in that way. You don't have to make an inspired kind of step in a kind of postulate to deal with it. And I don't know why that didn't happen, but it didn't happen. So I think we need to go back and look at all this stuff again. We can examine the results that we have in hand and find some issues to worry about. Even before Einstein published his first paper, there was work attributed to Lienard and Vigier. Actually, a number of people solved the same problem about figuring out what are the potentials in fields that are created by a rapidly moving source. And they all got the same answers. Historically, the names Lienard and Vigier have been most attached to it, I think because there's been a tradition in Europe where there's always been a lot of warfare, that if science could seem to show some kind of case where people were cooperating with each other rather than shooting each other, that they would feature that. So anyway, here we have a Frenchman and a German, and they have the Lienard-Vigier results, which give you the potentials in fields from a rapidly moving source. Now, you can look this up in any textbook, and there's some interesting things about it that you can ferret out by looking in the textbook. You will find that the Coulomb field is developed for the moving source, and it points in a direction that is not the retarded direction from the source to the receiver, but it's rather closer to being the direction from the present position of the source when the signal is received and the receiver, which is kind of a head scratcher. You wonder why that would happen. And it certainly does conflict with the corresponding results for what the radiation direction is. The pointing vector for the radiation points nicely from the retarded position of the source to the receiver. You never see these things on the same page in a textbook. It would be kind of alarming if they were on the same page. So there's something squirrely about that, or should I say dodgy about that. And because addressing it would require one to really change one's point of departure for the whole analysis, it just sits there and nobody pays attention and just close their eyes on that. So that is a problem, I believe, and we need to see if we can do better. That would be a check. If we do anything to improve the theory, that would provide a check as to whether we're going in the proper direction or not. I don't know why Einstein overlooked all of these things. It may be that he was a young man and he hadn't studied everything yet and didn't like math as much as he might have liked it. But at any rate, it got embedded into the culture that C should be regarded as a constant relative to the receiver of the signal, and that should be true for however far back that signal came from, and it's kind of crazy. Now, when I got out of school, having just written a thesis in special relativity theory, the first job that I got was at Vigier lab at MIT, and it dealt with a number of technology kinds of issues, and one of the issue, in fact, that I was hired to look at was the ring laser gyroscope. There were ring laser gyroscopes in development at that period of time. And I thought, oh gee, that's neat. I can see something, I can find out something about that from special relativity theory. And I tried and I tried, and it simply didn't work. It does not work. Complete flunk on that issue. The Signac effect is, in fact, an experimental challenge to special relativity theory. It advocates for a completely different way of saying how signals behave. And I've come to realize that what it's really telling us is that the speed of light is c relative to each successive little bit of matter that it interacts with on its way to the detector. So it starts out being c relative to the source. Then it meets some other piece of matter, it gets changed a little bit. Then it meets some other piece of matter, it gets changed a little bit. Meets some other piece of matter, it gets changed a little bit more. And eventually, it meets its receiver, at which point it has to be traveling at c relative to that receiver. That works like a charm. It doesn't matter what the Signac device is like, whether it's, well, today it would be a fiber optic gyroscope. That's been the penultimate development of the technology. Fiber optic gyroscopes have a little fiberglass that goes in zillions of times, and you put this into any kind of inertial guidance system. Did anybody come here on an airplane? Yes. Of course, you all came here on an airplane. You trusted your life to the Signac effect, okay? It really is trustworthy. And it doesn't matter what the geometric configuration of the thing is or anything. What comes out of that is a phase shift that reports rotation of the system in which the thing is mounted, and that output depends only on the rotation rate and the area that's enclosed by the Signac path. And if you try out what I'm proposing as a rule for what the speed of light is, that it's c with respect to each successive bit of matter that it meets, that works like a charm. It can be a rather complicated fiber optic gyroscope where you've got billions of little molecules of glass, each one interacting with the light successively. Or it could be a very simple one, it's a square one with just 4 mirrors in it. Or it could be an even simpler one than that with just 3 mirrors in it. Doesn't matter. Doesn't matter at all. The thing is really, really reliable. That's what it's telling us. So I ask you all, don't you think maybe we should go back to the beginning of SRT and use something based on that knowledge instead of that second postulate that was the thing chosen at the beginning of the century, and now go on 20th century. So one step in a rational direction, I would say, that would work in many, many cases, would be, instead of demanding that a situation be analyzed with c relative always to the observer, or c relative always to the source, which does not work. That's the Ritz proposal. Instead, imagine that it has to vary as the reference for c has to vary as the scenario progresses. And the best average value to think about would be the one that's in the middle. You know, make it c relative to the midpoint of this scenario, and you'd have a scenario where there was this all-important midpoint, and the source over here, and there'd be a receiver over here, and they would be moving always in some kind of synchrony throughout the scenario. And you would do your calculations as if the reference point were at the midpoint of the scenario. That solves a linear Vigier problem.
Can you put a mic on here? Some of the thing I can't hear.
My voice is rather soft. Yes, do you have a mic that would help amplify my voice?
Anybody got a microphone?
Yeah.
No microphone? Do we have a microphone?
Yeah, we have a mic.
Let me come a little closer. That was another reason for my trying to be here instead of there.
myself, you have a mic, and I can hear you, right? Someone can hear you.
Yeah.
I'm getting old, my ear is not very good.
Well, I'm suggesting that we change that second postulate, that we don't arbitrarily say that it has to be safe relative to the receiver, nor do we go to the other extreme and say that it has to be always C relative to the source, which was, that was Fritz's proposal, and that we failed early on, and that was made another contention. So we should look at another possibility at this point in history and see what happens. Now, I told you about that Leonard-Rickert problem, where the Coulomb force and the radiation signal don't come in the same direction. That's a painful problem, people just ignore that one. It's like as if a baby was born with its eyes crossed, okay? And that's kind of a sad situation.
Can you expand it one?
The pointing vector for the radiation goes one way. The Coulomb vector for the electric field attraction goes another way. Intuitively, you would expect them to be aligned, so they come from the same source. And in the Leonard-Rickert formulation, they simply don't. They don't align.
Could I ask a question about that? Is that essentially saying that the Coulomb field is not propagated, but is just there?
It might be somebody might
The
be
Coulomb field is not propagated, nor is the gravitational field.
Yeah.
They're just there instantaneously,
I don't
irrespective.
I don't believe anyone actually drew that conclusion, or I'm not aware that anyone drew that conclusion.
I thought that was...
But that's what could be taken from that result. That could be.
Well, yeah, the Coulomb field is just there. I mean,
Yeah, it doesn't propagate.
light is a variation in the field. So.
Yeah. Same with gravitation. It doesn't propagate.
Yes.
I just want to make sure that I understand what you're proposing. If I understand correctly, what you're essentially saying, the way I would put it in my own words, if I'm understanding correctly, is that you're saying the speed of light is constant in any reference frame viewed locally. And so it doesn't sound to me like you fundamentally need to change special relativity. It's more, we just have to look and keep in mind that we always examine our interactions locally, whether with light or
That's
anything else.
definitely step one. And step two would be then to exploit that in problems where you really need to look at long distances and not to assume away these subtleties.
Cynthia, do you regard homeopathic dilution, as an anachronism?
I do not know. I don't know anything about homeopathy.
But I could name for you half a dozen anachronisms, like my PhD student's experimental verification of astrology, the very profound Indian astrology, which are complete anachronisms, and which all these professors at Oxford and Cambridge are prepared to say, we can't possibly explain that, therefore it doesn't exist.
Well, that is certainly
That's an anachronism in your terms, is it?
anything that you're suggesting that something from another culture, as well as something from another time, deserves a second look. And I would agree with that completely.
Good, okay.
Cynthia, I'd like to say, when you say the two basic postulates, you're missing the most important one, which is that Einstein was a realist. He believed that there was an independent world. If there's an independent world, there's only one speed of light. And if you want to measure
There's a
it...
speed of light, and there's a reference point against which that speed is defined. There's always those two things.
But there's one world, so there's one parameter, there's one phenomenon. It's just like if there's one chair, then if I measure it from any direction, it's the chair. That's intrinsic in the idea that there is an independent, objective universe. If you build coordinate frames, measuring instruments, to measure that independent, objective parameter, then your result has got to be, if it's built correctly, a single number. And Einstein simply said, how do I modify my coordinate frame measurements to make that happen?
Right. The
So
question isn't that
the
question.
error is that
The answer
there is
is
no independent objective world.
I don't think that is the answer. The answer is that we made a mistake in figuring out how to transform from one coordinate frame to another coordinate frame because we relied on that assertion that the speed of light is c relative to the ultimate receiver, regardless of how long away it has originated and under what circumstances. So that's what we need to change. We need to realize that that was not the only possibility, and we need to look at the other possibilities.
Well, I agree we need to change it, but I think you're missing an even bigger point, so please go ahead.
Okay, where was I?
I think special activity is just a limitation, not a real the real situation. Because in any situation, the special activity also affected by gravity and everything. So it's considered as a limitation, not as an action.
That's right, we have a correction to make. It's not that we're going to overthrow the idea of signals and figuring out what the other guy sees based on what we see and so on. We're just going to try to make a better job of it.
You want your talk interrupted or have questions before the interruption?
Oh, interruption is better.
All right, she prefers interruptions, so have at it.
Okay, anything else anybody wants to ask right now? I suggested that as a better first approximation, rather than one extreme or the other extreme, that we should investigate what, if we consider the midpoint of such a scenario to be the reference against which we measure C. That would stand as a good average value. I mean, sometimes it's more like this and sometimes it's more like that, but on average, we could make a better model if we would write down the numbers as the reference for the midpoint of the scenario. So that is a quite simple thing to investigate. And it does take care of that problem that I told you about, the linear Vigier problem. That much of a correction is sufficient to make those directions reconcile. So it feels better, okay?
He's got the light.
All right, do I sound?
Hey.
Not working.
Somebody wants to ask a question?
I got some which takes 11 hours of recording.
That indicative any
I've
problem?
got to film you later. Do you want me to film later?
Is that the right way?
I didn't really realise. I think Richard supports Einstein. And he was messing me around last night. Yeah, he was joking.
It's on about the same committee.
Well, it doesn't actually do anything, but it's designed to feel like.
There you go. Is that related to homeopathy? Okay. Let's see if there are any more questions percolating out there.
It's working.
Okay, that's better then. So, in my opinion, sticking with
Like chalk on the blackboard. Oh, scratching sound.
in my opinion, staying with the way that special relativity theory was originally designed is counterproductive. We should certainly investigate alternatives. I've offered a simple alternative here to start with. I think we can do much better than we have. I think we can get rid of all the paradoxes that are in special relativity theory if we do this thing a little bit better. And I think the key to it is this, over-ambitious assumption that was at the beginning of special relativity theory that the speed of light relative to a particular observer was supposed to hold no matter how long the propagation distance was, no matter what else happened along the propagation distance, and that's just silly.
Well, the assumption was inertial frames, right? So that's already a restrictive assumption.
That is already a restrictive assumption. But of course, we like to handle radiation, and that involves acceleration, and so we have to give sometimes on those constraints to get everything that we want out of a problem.
But it sounds like the kind of situations that you want to correct for are ones that go outside of inertial frames, or do you have corrections that you want to make in relation to constant velocity
If we
moving
really
frames?
restricted relativity theory to inertial motions only, we couldn't do physics. Physics is about acceleration starting from Newton's time, so we need a little more flexibility than we originally stated in the beginning.
Right, but special relativity wasn't designed for that, and that's why we have general relativity.
Well, not necessarily. We would like to be able to do better on the simple problems, even in special relativity theory.
I see your point.
Okay, and I saw another hand, but then it disappeared.
Well,
Sorry, maybe that you are holding the microphone overturned.
no, it's right position.
Right position?
I guarantee you there's a little grid up here, and he's right, that must be the microphone.
You talked about using the midpoint as an approximate point of reference.
Yes.
Well, what would you do then in cases of astronomy, for example, where we're not exactly sure of the distance to the object that we're looking at?
Okay.
We're trying to figure it out.
Then I would start with an approximate value. I would start wherever I had to start with what we do know and see what improvement we could get by looking at it that way. We've been very, very high-bound, really, in insisting that it always had to be C relative to the ultimate receiver, no matter what the hell we were talking about. That just isn't the way to go about things. You got to give sometimes to accommodate to the realities of the problem and make some accommodation that gets you a better answer.
Can I say something?
Yeah.
I think one of the problems is the midpoint, because it's that definition of simultaneity that Einstein is really dodgy.
Right, I haven't talked to you about how you would find a midpoint. I'm only talking about how to think about the problem.
Okay.
But if you could do special relativity better and process signals better, you'd have a better chance of finding that midpoint. I think it's very rigid and hidebound to insist that C is C relative to the ultimate receiver, no matter what the hell goes before it gets to the receiver. That's overly rigid, and we should open our minds to other possibilities, and we should do a better job of investigating all those possibilities.
You know, what always bothers me is the insistence on uniform motion, because as you say, it's useless for physics.
Yes.
And all the examples that are used are non-uniform, like for example, muons.
Sure.
You know, being time dilated because of them. Well, they're certainly nothing to do with uniform motion. And also, to actually do the measurement, we have to slow them down to nothing. So if we're really doing an acceleration measurement, what
We certainly are.
And so, well, why bother with this uniform motion business? Why not just go straight into the... Does it matter that it's uniform?
I don't think it does. I think we can crack these problems even with acceleration. That was an initial assumption that they possibly get started in this area of research, but we don't have to stick with that.
But if we did change it, it's more the philosophy that would change rather than the equations or anything.
Well, I think the changes that will also show up in the equations.
Which equation?
I think all of them that are involved in special relativity will have slightly different...
Would we use Galilean transformations, for example?
I think Galilean transformations are pretty good, and I would bet that they're going to survive into the next century.
And we wouldn't need to use, time dilation and all that sort of
I
stuff.
don't believe in time dilation, nor do I believe in length contraction or any of it. All of that stuff is now suspect in my mind, and it certainly has to be reviewed.
So you think you'd see a Galilean
I think
future?
so, yes.
There's no reason why we can't use Galilean transformations, of course. Because we could just as conventionally choose C to vary.
Yes, you could. And it does vary in the sense that the reference for it varies. The reference for C is always whatever the most nearby matter is, in my judgment. So it passes through glass or whatever, it's going to be aware of those bits of matter. And I saw a hand there.
So, am I understanding correctly that Einstein may have fumbled his postulates or formulations without stating precisely what he means?
Right. Yes, that is probably exactly the way to put it, because he probably didn't at the time deal with the kinds of cosmic size problems that we are interested in today, the stars and all of that. In fact, people were only beginning at that time to discover that there existed such a thing as stellar aberration, which was the thing that excluded the other extreme assumption that the speed of light would be seen relative to the source.
And did it also not help that there were consistent geometries that were non-Euclidean? I mean, that question of the parallel postulate and the negation of it, would that have kind of opened the door for all of this?
Maybe for other people. I don't really think that Einstein was himself initially that deep into mathematics, but other people were. And so they would have perhaps carried the conversation in that direction. In fact, it was his friend Bessel that I mentioned, I believe, who got him interested in tensor math, because he would never have taken that up on his own. He just wasn't that kind of guy.
So are you also suggesting that you can do all of, can you do resolve these problems or do this kind of space-time math with just Galilean transformation?
That's what I think is going to be the end result.
Okay.
So that's a prediction, not a prediction, but that's what I think is true.
If I go back to that business about the Coulomb field not propagating, that's used as an argument, isn't it? The argument for it is to say that Lorentz invariance wouldn't work if it did propagate. I mean, I've seen that argument. I think it's I looked it up in Wikipedia even. I think it's in the Wikipedia article.
Well, okay, what about Lorentz invariance? I don't have any particular commitment to Lorentz invariance.
No, but if you did, I'm saying in the conventional view as present, if the Coulomb field did propagate, the Lorentz invariance wouldn't work. So to preserve that, you need the Coulomb field to be instantaneous, along with the gravitation.
And that seems to shoot down the whole idea, really, doesn't it, of relativity theory?
Well, it's just, it's to preserve relativity theory, you need that.
So one goes around in circles.
Yeah.
There are not circles here.
I mean, you still can work within the relativistic paradigm to some extent, even if...
We have to rediscover it and find out what it really is like.
So could there be like a logical problem with all of this in the sense that there's a like I said that again, but there's a logical misformulation of what we mean by invariance, and if we were to state more clearly and more precisely what these terms mean in terms of properties and axioms and stuff, would that kind of resolve it a little bit?
Yes, your statement says that we should do everything more carefully than we have done, and that's absolutely true.
I think you're in the right conference. I mean, most of us feel that all this stuff needs to be looked at more carefully.
Yeah. I appreciate so much that this community exists. They're wonderful people. Okay, we can show the other slide now. I have 2 slides. So we know about the efficient void there, and he represents Einstein. We do still love him, but we know he needs to do some growing up. Okay, I've been working on this for a long time, at least at 45 years, maybe more. And it's very difficult, as you can imagine, for anyone to publish this kind of information in any kind of mainstream venue. But I finally got a break and was able to publish a book. And there's a funny story about the book. This is a book about chemistry, because the truth is, if you can do physics a little bit better, then you can do chemistry a little bit better. And if you can do chemistry a little bit better, you can do chemical engineering a little bit faster. And once you get to chemical engineering, you're into something that makes real money. So the publisher is willing to publish the information. However, when I first submitted the book proposal, I had these subjects in the opposite order. And I had algebraic chemistry, origins, and applications. And within 24 hours, the publisher rejected that proposal. And I sat down and I thought, what's going on here? Why don't they want to publish this? And I thought, well, I haven't taken account of what their business model is. They're into engineering, and I should include the order of the subjects in the book. So I got the word processor, and I reordered the items in the proposal and sent it in, and they accepted it within 24 hours. So what's happened here is that all the deep physics is in the appendices, and all the applications are in the beginning, and that's how you get a book out. So that was an interesting learning experience. But it has things in it that touch on one of the earlier talks here about the substates of hydrogen, for example. All of that stuff, you can get some explanation for once you've somewhat revised your relativity theory. You can understand, first of all, that there's quite a lot going on in the hydrogen atom, and that Planck's constant is no act of God, that it is the result of all the things that are going on in the hydrogen atom. There's at least 3 things going on. There's the Coulomb attraction. There's irradiation because the charge is accelerating because it moves around in an orbit. And also the whole system shakes a little. And this is all caused by signal delay. That things don't happen immediately, that there is signal delay within the hydrogen atom. Now, when you take account of all of those things that are going on, you have, of course, competing factors instead of just one factor. You used to know only about radiation, and you thought the hydrogen atom would run down. But now you've got several more factors in there, and you can come up with a balance, because the signal issues cause a little bit of torque in the system, which pumps energy into it, and so that fights the radiation. And in addition, there's the overall motion of the system. That's called the whole thing of jitter. You've heard the word jitter before. well, it's a real thing, and it's caused by this phenomenon with the relativity theory having been done wrong, and you get it right and you find out that that happens. So all of these things are happening, and some of them are causing energy loss, and some are causing energy gain. At some point, there's a balance between all of these effects. And guess what? The balance comes out at the ground state of hydrogen. So that's worth knowing. In addition, there are other balance states that are lower down. There are substates of hydrogen. Well, those were mentioned earlier today, and they're discussed in the book. I believe they actually happened, and I believe we're, got a handle here on an explanation for why. As for elevated states, I now believe that those are actually more complicated systems, like n=2. That doesn't just mean an elevated state of a single hydrogen atom. That means a state that involves 2 hydrogen atoms. Same with n=3, and so forth and so on. That is a different explanation for why there are different overall system states, which when they fall apart, they dump radiation, and you see the lines that you see in the hydrogen spectrum. So, and that's not too hard to calculate either. So that's where we are. I think it is a powerful tool for figuring out what the hell's going on. And I'm occupied for the rest of my life with it. Any more questions?
So you believe in the 3 states that Richard was talking about?
Yes.
And you have a calculation for it?
Yes. Yes, it's all
Do you
in the book.
happen to have a description of an experiment that was trying to...
Well, I haven't been an experimentalist myself. There, of course, is a description of what this theory predicts for the substates of the hydrogen atom, and that's in the book, but I'm not qualified to pair that up with experiments. I'm just not the person. I need another person who can write to that subject. Yeah.
Cynthia, you talked about the second axiom of Einstein. We go to the first axiom, which is the laws of physics are the same in all reference systems. Is a corollary of that the statement, the outcome of an experiment is the same irrespective of the inertial frame of observation?
Yes, I would say so.
Thank you.
So are you saying that we should preserve the first law, Einstein's first postulate?
Yes, the postulate of relativity, the laws of physics are in fact the same for all inertial observers. We should just take a little more care in applying how we understand and process data. That we haven't properly put in there the way that signals get from one place to another place, and what really happens and how much time it takes and so on.
There's been a few arguments that going back to the 1900s, but often resurrected and sometimes by quite prominent people, that the second postulate is unnecessary because it comes from the first postulate. What's the, do you know anything about that kind of argument?
I do not. Can you tell us a little more about what?
I don't know the argument totally, but I've actually been in access where people gave it. And I can find out more about it and write to you.
Well, it has the idea to it that you don't need a postulate, and I believe that that is actually a true idea.
But you didn't need the second postulate.
You don't need it, because if you know how to handle those differential equations and apply boundary conditions, you're going to get the answer for sure.
No, that was an argument as early as 1906, but you remember the talk?
Yes.
He was one of the people who came up with it. But there was somebody quite well known who came up with it as well. It's a Cassie's speech. One of the keynote speakers. I'm trying to think who it was. It was somebody with a big name, who came up with it. Was it, I'm trying to think who it was. Okay, it'll come to me later. We'll do that.
Anyway, I went back up and say that one of the things that most dismays me is that people didn't just start looking at this problem like they would with any other problem that involved differential equations and boundary conditions. Why not? solve differential equations.
Well, Maxwell equations changing?
No, Maxwell's equations are equations, and those kinds of things are invariant. That's it's a physical law. So what will change is that you will, first of all, propose what kind of solution you're looking at, and I say you should look at a pulse, and you'll observe that when Maxwell's equations work on an electromagnetic pulse, the first interesting thing is that the pulse unwinds and it turns into a little wavelet. So right away you're looking at evidence there that should make you wonder, what in the world does speed of light really mean? This thing is not only moving, it is also changing shape.
Yeah, dispersion, that's the phase particle question.
So it's, I think, a lot of interesting things to be said there. I don't know why they weren't said 100 years ago.
Comment. Do you assume that quasar luminosity is caused by gravitational shock waves rather than Doppler expansion of the universe? One can postulate
I think that's
duality between Newton and Einstein's gravity, and then you can, so there's a local and instantaneous effects of gravity, and it looks like the reasons why the trans-Jupiter rings, planets have rings is explained by this. Anyway, just a comment.
Yeah, well, I think that should all be looked at again, because everything having a non-general relativity did in some sense presuppose special relativity, and there may be things in there that would be upset if you modernize special relativity in any way. I think that can be done. I don't think it's I don't think it's a daunting and impossible problem, and we should have the courage to go do it.
Thank you so much, Cynthia.